Okay, I'm now starting the recordings. Yufan, please start.
Okay, hello everyone. Today's paper is sequence-to-sequence visual debugging tool for sequence-to-sequence models. It is published on the journal VAST IEEE 2018, and it is awarded the best paper honorable mention. And there are 6 others. These others are all come from the visualize field or natural language processing fields. And the first other is a researcher and a data scientist at IBM Research. And other users, other authors may come from like company Google or from the university like CMU and Harvard and Cornell. And today we will have 5 parts. First, I will briefly review for the sequence-to-sequence models. Xiangling had just introduced the sequence-to-sequence models last week, and I have a very easy question in the first section. And in the following section, we will have some real-world examples to check what the system needs. Okay, the first is the review.
By the way, so I just mentioned from this week, maybe a few weeks ago, so we asked the presenters and speakers to prepare several questions for the audience to answer, and so anyone will be can be volunteer to answer those questions. And also, if there's no volunteers, we may randomly pick one to answer. So I hope that I can focus on to Yufan's presentations. Maybe you're the one who will be selected to answer these questions. Okay.
Okay, first we have a short review on recurrent neural network. We know that the recurrent neural network, typically for one neural, we have 2 input. The first input is xt, that means in the t time step, and the ht, that means the hidden state t minus 1. So in every neural network has 2 input. One is xt and one is xt minus 1. And the hidden state ht minus 1 just come from the xt minus 1 until the x1. So the recurrent neural network is very simple architecture. And we also, Xiangling also discussed about the encoder-decoder architecture. The encoder-decoder architecture is a bit complex. It first have one recurrent neural network here, and after get the hidden state of each xi, then it will have conclude all the hidden state to a context, and then it have a decoder architecture. On each step of the decoder architecture, it will get the final result. It will get the output vector. So the encoder-decoder architecture is actually encoding a source sequence to a vector space and then decoding out to a target sequence. So here is the question: why we use the sequence-to-sequence encoder-decoder architecture, not the typical recurrent neural network? The hint is that why there existing a start and a stop sign.
So maybe I can clarify the question a bit. So the question is that why use sequence-to-sequence model are. So the question is that says for what applications, for translations or what kind of other tasks? So maybe I suggest that maybe you can copy and paste the graph on the previous line, and that's the audience to compare. Yeah, you can copy and paste this graph and here. So you can see we have 2 structure, right? So the idea is that the red points are the input and the blue points are the output. And basically we want to giving the input sequence and generate output sequence. And the question is that why are we choosing the sequence to sequence model of the RM. So that is Yufan questions. Maybe I would, so my follow-up question for Yufan is that, so is there any indicated applications for comparing these two models? I mean, implicated application, for example, the model translation factors.
For the traditional recurrent neural network, there's many sequence to sequence. There's also many sequence questions like machine translation. And now machine translation want to use sequence to sequence model. So why for the same application, sequence to sequence model are better?
Okay, so okay, so maybe I will rephrase the question a little bit. So from Yufan's question, Yufan is basically saying that for there's anyway, there's translation sequence to another sequence in application for example, the machine translations or the other anything, maybe the price prediction for stock anyway. So you can claim that the sequence to sequence model is actually better than the R model. And he has asked the audience for why. So is there any audience or volunteers to answer this question? And there are the things you can choose the things there. So why exists a start and stop? Okay. So any volunteer to answer this question? Okay, if there's no volunteer, please randomly pick the audience.
Maybe Xiangling.
I think one reason might be like for example, the context vector has the information for all the input sentences, and then later in the decoder part, it can look in all, and for the start and stop, maybe it gives it it makes it more flexible.
Yeah.
So you find, so does your model include a bidirectional RM or single directional?
Yeah, you can use bidirection in the sequence to sequence model.
I mean, yeah, so this means bidirectional, right? So that means in your questions, there's supposed to be other links coming back from the later token.
Yeah.
It is still possible, right? Okay.
Yeah, yes.
So Shani, would you please make your answer a little bit precise? So what is your guess? What is your answer?
Then it just makes it more flexible. You can have different lengths of input and output.
Okay.
Yeah, I think this is the answer because now you didn't need just the same length of the input space and the output sequence. For the RN, you are definitely want to have the same length of the space because you can use the pad to make the sequence different, but you can't use like a fixed size of the output space. However, in a sequence to sequence model, you can use a start and a stop length to make this output more flexible.
Okay,
you do not need the pad. You do not need the pad. You just use the start and the stop sign in the output space. It will
maybe from the input space, you still have some pad, right?
Yeah. In the input space, you cannot. You also do not need to use pad because the recurrent neural network is just the same neural in every token.
Yes, then neural. So I mean that when you have a token sequence like that, so there's no need to put any padding because when you design a model, you have to usually we need to have a fixed length as input.
Yeah, usually we need to fix the input length.
Yeah, so technically, when we feed a sequence into the model, after 早上好 these two tokens, and they're supposed fixed length is 10, we need to have 7 paddings for them. Am I right?
Yeah.
But when you have the encoding information, for example, we have encoded the sequence of 早上好 into encoded embeddings, and those paddings actually takes no effect. Or you still have some effects there?
In usually case, you can just fix like 10 words. So if it is less, you will just pad. If it will more, you just cut them.
Yeah, I'm asking in scenario. I'm asking about the scenario that when the token just giving this example, there are 3 tokens there, and the 7 left for the padding token. And will these 7 padding tokens will have any influence on the and will have an influence on the final embeddings?
No.
It
They will
likely.
not. Yeah,
Okay.
they will. Yeah, keep the same with the final words if you use the pad.
Okay, so I think Yufan these are very great questions to compare the RN, even for bidirectional RN. I hope that if anyone does not clear about what is RN, you can go through Xianling's videos, or maybe you can ask Yuchen's suggestion and advice, or check it out on the internet as well. But anyway, so here's a very clear point that compared to RN models, the encoder-decoder architecture has more flexibility, as suggested by Xiangling and Yufan. Yeah, that's Yufan. So, is there any questions here? Okay, if there's no further questions, please proceed.
Okay, so we will look a bit deeper on the translation model. First, we input a vector ni. This is a red dot in the picture, and then we input to the RNN model and get output size of no vector. It is the blue dot I can draw here. And next, we go through a fully connect layer FC, and then get output of vector NC. This NC represents the number of the categories. And then after a softmax and argmax, and we finally get the category index. Here is get the label index. Then after int to string model or into string architecture, we will get the finally output word or output character. And finally, this output word will just input to the next state. And then we will repeat this process to get the final sequence result until it receives the stop flag. So it is the typical procedure of the translation model. Any problem here?
Yeah, so I also would like to raise these questions. Is there anyone, including FFE students, you feel free to ask any questions about this architecture. I think this model is supposed to be an important basics for all the follow-up visualization, because this is the deep learning architecture, and all the follow-up technique is designed towards this architecture to showing a lot of its properties.
I have a question. So you are saying NC represents the number of categories, but can you be more specific about what is categories, and is
that's a good question. You can maybe have tried to introduce the concepts of a category. So I think that is an important concept. Seems missing on these slides.
From my understanding, the category means like the number of the words, like the dictionary. You just try to for the machine translation. You want it. You from the Chinese to the English, then the category may be the English word, the traditional and common English words dictionary. And the NC means represent the category of this dictionary.
Maybe I can complement some of the idea of Yufan. So basically, there's a fully connected network, right? And given a fully connected network, they usually have a soft max layer. So as Yufan's picture, I'm sorry, Yufan's picture here. So suppose we have vocabulary of English. That means for the model, it can only generate the words in defining the vocabulary. That means if the vocabulary size of it is 10K, it means that the model can only generate an English in that 10K vocabulary. Once we can large the vocabulary size to 100K, so we have enriched categories to those. So basically, Yufan's category just makes the vocabulary, right?
Yeah.
So here after the softmax, it will predict which category or which word is the most likely word to be generated, right?
Yeah.
Suppose you have 10K categories, and if the model finds after softmax, it finds the 10th category have a large probability like 0.6 or 0.8. So usually we may to pick these words as the targeted category, and this category corresponding to a vocabulary. For example, giving the word 早上好, and the first category could be corresponding to the word good, right? So that is basically what you means.
Yes. Okay. So
okay, any questions here on these slides?
Then what's the difference between this number and the index?
Index is the number, like one. This NC is a vector, like maybe if the vocabulary is 10K, this is a 10K vector.
Okay, I see.
Yeah. Okay, so so we will go back to the attention. Xiangling have mentioned attention last week, and we just see this picture, and that is we in the last week we are curious about the W because the W actually mentions the relativeness between the hidden state 1 and the hidden state in the decoder architecture. Now here is a bit deeper picture to show what is attention. Here is two hidden state. There is two hidden state. The first hidden state is in the encoder architecture. In this is HS. And here is another hidden state is in the target, so it is HT. In the encoder, we call HS, the S means source, and the T means target. So if there is the two hidden state. So how to calculate the attention score? Typically, I have just mentioned before, we use the dot product to just get the relativeness between the HS and HT. Sometimes we may use a better architecture, better forum to get the score. And then the AT is actually a weight. So they just multiply with HS. Follow this picture. You multiply with the HS here. You get the weight and then multiply with the HS, and then finally get the context. That this context means the means here is this here, this context. This is the context, and then you concact with the hidden state in the decoder to concat them to a final final vector, and then goes to predict the word. So in this architecture, it will compute the similarity or relativeness between the hidden state HS and the hidden state HT, and then combine this information to predict the final words. So in this question, in this scenario, because you know the zao means in Chinese zao means actually in English the morning. So if we use the typical architecture, the zao mean this word will not output the good, because zao actually means morning. So it will much good to use attention to pick up the best word or best match word, best similarity word in the encoder space. Like in this case, that means if you predict the morning, this weight will be much high. That means the model will much look at on the word 早, not look at the word 上. Okay, so any question here?
I have a question here. So, so basically, can you go back to the previous slide? Yeah. So here, so I would like to link your order architecture with those attention structures. Maybe my memory is a little bit fading here. So what is the role about the embedded vectors? What is the role played by the embedded vectors? So do you remember we will have autoencoder, encoder and decoder architecture, right? So the decoder architecture is basically the generator, and the encoder architecture actually will generate this embedding vector, and then we expand the embedding vector with the decoder to generate a sentence. And here, basically, you are showing that for each tokens in the embedding architectures where you have a relevant, we calculate a relevant score or attention with a specific, when we generate a specific tokens with the decoders. And here I feel a little bit missing for the role played by the embedding vector. And what is this embedding vector playing a role in this attention architecture?
I think you are question about this vector context.
Yeah.
Actually, in some case, it use the CLS to move this vector. It will not act actually, because this state is typically the same with this state, because there's no input here. We just use the same final state here. Yeah. So in some scenario, we also put CLS in the beginning, because this is a bidirection. So this we will put the CLS in the beginning. So CLS is not important here. Typically, we just use the same vector as the final state.
Yeah, I understand CRS, but maybe you can be more specific to the other audience that what is CRS and what role played by CRS.
CRS means just conclude all this information in the encoder. So typically it will be this neural.
The output of the last input of neural.
Yeah. So, but I also mentioned that if you use the bidirection LSTM or RN, you can just put the CLS in the beginning, because it is a bidirection. No matter with the position of the CLS.
My follow-up question is that since if it is a bidirectional architecture, and we're supposed to have two series, right? So the one output by the last token and the one output by the first token. So if that's the case, which one should we choose?
Like in birds, we will use the first CLS. And typically, I just mentioned the last CLS is just the final state of the encoder layer. So we typically didn't use it.
Maybe it's also specific to the retraining task. Right? For birds, maybe the first token, the output of the first token will be using in more play a better role or a more important role in the loss function. Might be. Okay,
Yeah, I think it's just to replace the 0 state as the COS. So typically we will use the use the first state as the COS. We didn't use the last state of the COS as the COS.
So basically, the attention architecture is an improvement of this encoder decoder architecture. So not only before attention layer, attention is actually a paper mentioned in 6 years ago. The paper name is called Attention Soil Need, and which has received maybe 10K, more than 10K citations up until now. This is very popular paper, and there's many blogs to rephrase and reinterpret the idea. So, Yufan, would you please go to the previous slide? So, based on the architecture of encoder and decoders, the attention layer actually introduced one more part. So, we will still have some embeddings. This embedding could be a CRS, as introduced and suggested by Yufan. And in addition to the CRS, there is supposed to be an attention layer to compare, to give it a position, and the token to be generated. We are going to look through all those all those input tokens to see which token in the input is more relevant to contribute to the generation of the to be generated token. Okay, I hope I make myself clear. If there's any questions,
I have a picture here. You can refer to this picture to see the attention between the encoder and the decoder. So for this picture, the encoder, the decoder, between the encoder and decoder, there's an attention mechanism. Here, the attention is to combine the information in the encoder states. Okay, I just introduced in the beginning, from the beginning. First, we have the words. The words maybe like 早上好, 早上好, and then we use embedding. The embedding may be like the globe embedding or typical embedding or preaching embedding. And then after embedding, we will go to RNN or LSTM neural networks to get encoder states. Here is a latent vector, a latent space vector. So there is the problem is that whether the encoder is good or not depends on the encoder states is good or not. So if you prove that the encoder states is good, and then you will think that the encoder is good. Okay, so after you get encoder states, you go to the decoder. The decoder is from this side to this side. The encoder is from this side to this side. They are different. From this side, you first input the start signals or start token, and then it will first have a word embedding, just like the encoder, and then get a decoder state. The decoder state also, the decoder is also LSTM or recurrent neural network RNN, and then from this decoder state, you will get a contact state. This contact just I mentioned, contact with the attention and the decoder state. Let's review here. This is a contact vector from the attention result of the hidden state in encoder and the hidden state in decoder. So it is concat two vectors to get a context state. And then this model uses the context state to finally get the final predict the word. And then he used the final predict the word to predict the next word and repeat this process. Any question here?
I think it's very clear here. Any questions you propose to clarify? Okay, if no, let's keep going on.
Okay, so now we have another, if we have finished with the encoder, decoder, and the attention. Now is the fourth stage is the prediction. So if you get the, you should remember that I have mentioned you first get a label index. You you first get an NC that represent the number of categories, and then you softmax it. But the result of softmax may be like here, like if it is the 4 words, maybe it's like 0.1, 0.2, 0.3, and 0.4. Okay, so for Argmax, you will just get only 1 word, like the highest possibility. But in the actual process, we will just rank this word, rank these 4 words. For example, this A, B, C, D. So this model will output that D, C, E, A. The D is the most possible word, and the C is second possible word, and the B is the third possible word, and the A is the most impossible word here. So the prediction is not only 1 word, but actually a rank. Like maybe you choose top 3, and then you will have 3 possible words like A, B, C. Then it will go to a beam search. What is this is the 4th stage prediction. It is got a top 3 like A, B, C. Then after this 3 words, they will go to a beam search. What is the beam search? It is related to a sequence prediction. Because this is only for 1 word, then you will get another word. This word will also get a top 3. Maybe like 1, 2, 3. So these two possible lists will need a beam search to get the most possible sequence. Like you may get the A and the first, and you may get the A second, or you may get the A third. This sequence will also get a possibility. Like for example, maybe this possibility is 0.8, and this possibility is 0.1, and this pair will have a 0.1 possibility. And then you will, if you use the beam search, you will choose like you will also choose like top 1. Then you will choose the first pair to become the final prediction. So this is the beam search. Okay, any question about here?
Yeah, so I think Yufan did a job to explain it, but I have a small comment. Maybe I raised this comment too quickly, but I hope, but I'm afraid I may have forgot this. So I think you have a very good explanation to draw on this, but your presentation will be even better if you make that into an animation slides. Right. So that will be chance more make people more easy to follow if there's animation. For example, we have several sequence, and each time we just choosing the top n. Here is 3, n equal to 3. Each time we proceed with choosing the top n subsequence to further proceed. So this is more like a gradient algorithms to going on. And basically, you find it's introducing algorithm. So beam search is basically a select algorithms, which is I think it can point to the category of gradient algorithms. And when we show the algorithms or interpret algorithms, the animation might be a useful tool. Very useful tool to make the interpretation. Okay, so here maybe I summarize Yufan's interpretation of the beam search. When we have a generation, so it have a lot of possibilities. For example, maybe the first word. So here, maybe I start with some function a bit. So there has a lot, giving the decoders, we have many possibilities. So basically, it is also introduced by Xiangling in last week. So they have a lot of possibilities. So maybe, so we now, from the human perspective, we now good morning, right? So I remember there's 3 tokens. Good morning, but somehow in the first choice, when we select we need to generate token by token. So here, it is possible that the first token, good is a candidate. There's other candidate like morning, or outdoor, the input is somehow, or there's other possibilities like what maybe better, something like this, or afternoon. So suppose we have a vocabulary on that very limited words. So maybe if we just look into the first token, the probability of good might be only 0.7, or maybe only 0.4, and while the word good morning maybe 0.5, and the word better afternoon maybe 0.1, 0.1. So in this case, if we pick the highest token each time, we may not generate a sentence like good morning instead of morning good, something like this. But we know that it's not formed formed to the conventional English. So, but the next time, if we look into the subsequence of good morning, and the consecutive two words now can raise the probability into like 0.7, while the another sequence like morning good may drop these candidates into 0.3 detectors. So here you can sorry, I don't know why I just keep misnaming Yufan interpreting showing that the beam search would like to break provide a trade-off between looking into two localized candidates or looking to two global candidates. If we look into all the candidates, it is definitely computationally expensive. If we look into two localized candidates, definitely we were likely to generate a sentence like morning good. So the Bing search will keep looking into the most promising, the most localized promising subsequence, so that I can generate a sentence like good morning. And all you transfer show the steps and the top three, the first top three candidates and the next top three candidates are all trying to solve this problem. So is there any other questions? Oh, if not, let's keep proceed. Thanks, Yufan.
Hello, can I ask a question?
Yeah.
So every time when you find the top three candidates, will you renormalize the probability, or you just keep it like that? Because your probability is multiplicative, so it will decrease a lot if you have a long sequence then.
But anyway, each time we're just choosing the top three.
Yeah.
But what do you mean by renormalize? I didn't see any necessity to renormalize the score because all the candidates were multiplication.
Because you eliminate the rest of candidates, so
yes.
you only keep the top three, then you might be taking each candidate divided by the summation of the top three candidate to renormalize it.
I think we do not do that, right, Yufan?
From my understanding, when you use the beam search, you will recompute the sequence probability, maybe like the max likelihood.
Yeah. But rule of expansion is not just the. I understand we need to recompute because the probability of one token and two tokens or three consecutive tokens were definitely different. I think the rule of expansion is that since we will remove some candidates, whether we need to renormalize the overall max probability.
I get his question, get her question, but actually we didn't need to use this possibility in the beam search. Because we use because you just need to choose the top three, and then you will get many possible sequence, and then you compute the sequence possibility, but not just multiply all the tokens possibility. That means you just didn't if you use the good morning possibility, you not just multiply like 0.4 like for the good, and then the morning maybe like 0.7, and then you get the 0.28. But
yeah.
here is wrong. We don't just compute the here. We compute the sequence possibility, but not just multiply the token possibility. We use the max likelihood to compute the whole sequence possibility. From my understanding,
I think it means like this. Given the first word is good, then the second word is morning, the probability. What's up?
Yeah.
Yeah, I understand there is conditional probabilities, but I still, Yufan, will you further explain why the 0.4 plus 0.7 way will not be used? Because
this
forming,
is not conditional possibility. This is just the morning possibility.
but this morning is generated based on the first token is choosing as good, right? You can see there's a link. There's a link. Can you see my annotation? I use it to read. So if we want to generate the word morning, it is based on we choosing the token. We have already choosing the token good in the first position, right? Because there is a link there. If we choose good, then the weight of link will change. If we choosing the morning, in the second tokens will not be morning anymore. This is likely will not be morning because the probability on the second positions is additionally based on the what we're choosing on the first one.
Yeah, maybe I actually didn't look very deeply about the beam search. Maybe
maybe there's open questions because my memory kind of fading on this part. It's good you raise this problem, and maybe I finalize these slides regarding Yufan's question. So I think we do not need to eradicate some of the candidate tokens because we never know what tokens we will choosing in the third and the fourth positions. So I think it is not kind of risky for us to re-summarize or to renormalize all the candidates. And I think just consecutive multiplications and just do his work.
I will introduce some numerical issues. For example, you have a sequence of length 200, and then you multiply all the 0 point something probability together, you will get a 10 to the power of minus 200, this order of magnitude number. So that will introduce some numerical issue. That's why I think it may be good to renormalize, because at every step after you choose the top tree, you do not look at the rest of candidates. You think you start from here, then select the next possible sequence. So yeah, I think it's some kind of trick to.
Yeah, but I think you're right that they may incur some numeric error. But I think eradicating some of the candidates may not the best remedy to addressing the numeric errors. Maybe each time we just in order to avoid the numeric errors, we maybe just multiply the probabilities by 10, etc. Just give it a constant instead of making these numeric these numbers disappear. Okay. So Yufan, please proceed.
Okay. So after you understanding the whole architecture of the model, you will think about how to visualize or what to visualize. For example, if you want to check whether the encoder is good or not, you need to check whether the encoder state is good or not. If you want to check the attention is good or not, you need to visualize the score of the attention mechanism. So if you want to the same with the prediction and the beam search. So this is the what this paper do. It just visualize the encoder state visualize the attention score, visualize the decoder state and the prediction and beam search. Then the user will see whether this part are work well or not. For example, for the encoder state, because this is a very high dimensional vector, you can't, human can't actually know whether it is good or not. In this paper, he used some techniques. Actually, he just okay, we will use the example to show this. For example, here is an example. This is a model from German to English. The source is here, and the gold label is here. The longest journey starts when it gets dark on the street, and the prediction, the model prediction will be here, and this clearly is there's something wrong on the prediction, and so there is a 5 question on the model. Is the encoder okay or not? Attention, decoder top K, or beam search. And here is the model. Let me show. We can see the encoded words is just the German word, and the first line, the first yellow line, this line is the possible prediction as the most possible prediction. And you can see here is the wrong because the 2. And the first we will look at the encoder. So we choose to change it to the encoder picture. And then we will see a graph. This graph depicts the high dimensional space of the encoder state. So these are the words in the German. And then you will check whether these German words are encoded right or not. So how to see the encoded state is right or not? This paper uses other sentence. That means, for example, in this darker, in German, in English, it means dark. Here you can see that this neighbors, this darko will get an encoder state. This is a point. This is a high dimensional vector. And then he compares this high dimensional vector or like the hidden state with other hidden state, with other sentence hidden state, and to see whether it encoded right or not. And then you can see that many neighbors in this circle, they just the same word as darkos. That means this encoder state is right because other sentence also have the same encoder state or encoder vectors. Some maybe you can see some words are maybe didn't true, but most words are just the same word as darkos. That means
so it's basically showing whether whatever the word, I don't know how to pronounce it, the downcodes, suppose that it, given that whatever position the downcode appear in a different sentence, if they can consistently project into the same high-dimensional space, you believe that it is correct reading.
Yeah.
But is that contradictory to the idea of BERT? Because I think one of the most famous examples is for the bank example. So the bank, for example, I borrow some money from the bank, or I walk along the bank to see beautiful rivers. So giving these 2 sentences, so what bank actually have different semantics. They are supposed to be projected in different embedding space.
Yeah, this is another example, and this is different from today's architecture. Yeah.
Basically, so in their approach, they believe that giving the word downcodes, and it is supposed to be giving different sentences, and those downcodes will be embedded in the same space or same position.
Not the same, they are very near, they are in a neighbors. That means they are close to each other, but they may have different meanings. Could you get this? They
I
may
got it.
have different meanings, but they close to each other because
This
they
is
are
basically the output hidden state of the embedding layer.
encoder layer, not the embedding layer. The
Oh,
encoder
all
layer.
right,
The
yeah,
embedding
okay,
layer
got
is
it.
different. Yeah.
The encoding layer. Yeah.
Yeah.
Okay.
So this is the
So
encoder.
here I still have questions. Uh, so if we look into, we can just calculate the average distance between its encoding vector to calculate the possible bug. Right? So my point is that if all the vectors of the encoding layer is concentrated on a small cycle, it gives more confidence. But if it's distributed on a large cycle, it shoots a lot. Okay, it is distributed in such a way. In this case, it means that this encoding does not work that well.
Maybe. Actually, I'm not quite sure.
I think if that is the case, we can just statically write a rule to check the possible encoding of it. No need for visualization. But anyway, so it's good for us to visualize these problems. By the way, may I further ask how do they perform the dimension reactors?
I use
Because for
they said they use the TSNE. Yeah, I actually didn't know this algorithm.
I think Xiaoling is supposed to be an expert for this algorithm.
Yeah. And do you know what does the green line means?
Green line. Oh, this is the sequence of the word.
Also, they just mean the
Order.
Sequence. Just the
Oh.
sequence. You can change it to another. Yeah, this is just a sequence so from the first word to the last word.
Oh, do the alternative represent different sentences? Oh.
Yeah, the y-axis is the position of the word. This is the first, this is the second, and this line is the y dimension projection of the wording.
So basically, it will try to project into one dimension.
Yeah. Sometimes they project to one dimension, and here is project to two dimension.
Oh.
Okay.
Okay. So from this point, they think the encoder is not is good because they encode to same Darkos neighbors. Okay. So then how about the decoder? Is the decoder error? So the decoder is a bit different because the decoder, remember the decoder will output the next word. So if you want to check this word, you want to look at the last step of the decoder. You not look at this step of decoder. So here we used to want to we check the get. Okay, we check the get because the word is get to the street. So we want the next step of the get is dark, but not to. So we check the decoder vector, the decoder hidden state vector, to see whether its next step is dark or not. Here we can see that the most possible word next to the get is dark. Could you see this? So they think that the decoder is good because they get the decoder's hidden state gets the right result.
Then why did they predict 2 in the first place?
Pardon, please.
I mean, why did it predict the next word to be 2 in the first place? Because since you mentioned that the next most possible word should be dark.
I didn't get your meaning.
I mean, here you are showing the next possible words to be dark, but why did it predict the next word to be 2 in the first place? Because the top one
Is 2.
is 2. Why is
that? Here we just prove that the decoder's hidden state is true, not false. But there still remain three attention, top key, and beam search. So maybe some error in the attention, top key, and beam search.
Okay.
Yes.
Please go.
So I explain again. We get a decoder hidden state vector. This decoder vector, we want to predict dark. So we check whether this hidden state, the neighbors of this hidden vector, and see the most sentence, the next word is dark. That means this decoder hidden state vector are possibly to predict dark. So this means this decoder is good. Any problem?
Here, my interpretation, I think, very similar to the encoding part. It is showing that giving a dark is the encoding vector are very consistent. Right? But then to show get the dark will necessarily follow gets. Right. Because giving a few samples, so these samples are taken from the training samples.
Yeah, here is just the decoder state here. This state is good, but did not mean the context state is good or not, because the context state related to the attention.
So basically, you're looking into the training, maybe training may tested. Maybe I guess it is training. So in many training samples, as long as there's a dark, the decoding space of the dark are very consistent and concentrated in a very small space.
Actually, the decoder state of get, not the dark. So it's
okay, so your point is that the decoder space with get are very consistent.
Yeah.
I mean that whatever can appear in the sentence, that is decoding vector looks very similar with each other.
Yeah. So get's decoder's hidden state will have very consistent neighbors.
And by the way, the decoding space, will the decoding space involve attention canon, or will the attention distribute to the decoding space
The attention will not influence the
decoding space.
decoder space. It will only have it will influence the context state.
So basically, the decoding state contributes to the attention declaration.
Yeah.
So they can confirm that. We can say attention will not contribute to the decoding space, decoding vector. So if we want to have a final output, so there are multiple ways to combine the decoding vector and the attention mechanism.
Yeah. Okay. So this is the decoder. The decoder seems quite good. And then we will go to the attention. And this is the attention here. This is attention. And we can see that for the two word, the attention is mostly from the DACO. That means the attention is good because attention marks that we need to we need to translate the DACO word. That means this is good because yeah, the dark code is actually what we want to translate. So why it translates to the 2? So it finally goes to the problem of beam search. Here we can see the beam search tree. Here. Oh, sorry, we just forgot the top K. The following graph is the top K. Yeah, after we get the, remember we now get the contest state. Then we will go to softmax and graymax to get the top K. And you can see in the top K here, the most possible is 2. And the second possible is dark. And they are quite the same possibility. So that means the top K is quite good. The model actually he is struggle with the 2 on the dark word. They are struggle on these 2 words. Could you understand this? Attention and the top K. Any question? Okay.
But the token before dark is very different, right? So you mean the top K here, one sentence is the top, right? And the second sentence is supposed to be another.
No, this is the top case means in the top word. It's not.
Oh, I got it. Here.
Yeah.
Okay.
Yeah, top word. Then for the beam search, they will get the top sentence. However, in the beam search, you can see that actually the dark is no appearance of the dark. So the question is on the beam search. We may enlarge the beam search size to let the model consider the dark word.
So the beam search is top 2, but you're always choosing the top 2.
Top 4 actually, you can see.
Top 4, okay.
Yeah.
So here, if it is top 4, it is supposed to choosing. So when it was for example, given this candidate, right? So this candidate here. So when it would reach here, what is the other follow-up, the other candidates there?
It's not. So I think it's just the problem, just Yufan put forward. Actually, it computes the sequence possibility. It's not like goes to a word and then computes the 3 top K. It's just compute the whole possible sequence and then get the final score.
Yeah. So for example, suppose we have subsequence. I'm showing here subsequence of what? So I'm using SS1, SS2, and SS3, right? So suppose we choose the top 3.
Yeah.
And in this top 3, we supposed to using this one to predict SS1 plus maybe T1 and SS1 plus T2 and SS1 plus T3, etc. So we will have similarly we will have 9 candidates here. And
from my understanding, it's not true.
Okay.
They are just consider all the sequence and then get
all the sequence.
Maybe,
so, but we generate token by token, right? So, for example, when we reach some sequence, like the longer the travel begins, it gets. So this is one promising sequence, and there's another promising sequence, and we need to amend the follow-up tokens one by one, and then we've got SS1 plus get a subsequent S1 plus T1, and then calculate its score. Right, and then we rank those subsequence and choosing the top 3 further, and we reiterate this or repeat this process iteration by iteration. Am I right, or I have some misunderstanding?
Yeah, I also didn't got quite sure. From my understanding, it's just like you just use like top 4 or top 3 all words, and then you will have like 4, maybe like 4. This possible sequence, and then you finally compute all the possibility of all the sequence, and then get a final.
Then it will be combinatorial exploration, right? Suppose they have 100 suppose the sequence of 100, so it will be the before to the power of 100. So it is not possible.
Yeah. Maybe I didn't quite not sure about this.
Actually, do you remember the big search evidence?
I think from my understanding, at each step, you only consider
Four, right?
yeah, 4 times the vocabulary you have. So each step.
Okay,
Yeah.
so maybe in this case, when you get the sequence here, the result of gets there's no
dark there.
But
yeah.
but why do you have like 4 or 5 sentence here? If
Here is from the different sequence. Let me clear. First, it have 4 possible token, and then actually I didn't quite sure about this. Maybe
my guess is here. So maybe when it arrived to get here, it also one candidate here, and one of the candidates supposed to be on here, and another candidate is supposed to be here. Right. So these 4 candidates are the most important candidates here.
yeah.
And then each tokens, for each candidate, it will derive 4 offsprings. 4 offsprings means that we're at 4 most potential tokens attach the 4 of these most promising tokens to that and derive a new subsequence. And this sequence will give you a score. And based on Yufan's interpretation, it seems that after we attach the dark to the get, it does not rank high. Suppose we have another candidate dark, it may appear in the top 16, but it may not rank into the top 4. So the candidate token dark is eradicated.
Yeah. Maybe.
And what is solution? Suppose we know this problem, and what is the solution?
He said maybe enlarge the beam search size. Actually, I didn't quite sure about this beam search. So maybe, but he didn't actually, because this is a visualizing tool, he didn't give a solution about if there are some problems. He just say if you can see what is the problem, and you will manage it by yourself.
Yeah, it is similar to Xiaoling's work here. We just show what it is, but we haven't given a remedy view.
But I'm still somehow
please.
confused because why like the combination of gets dark, the probability of gets dark would be lower than gets 2. Otherwise, the gets 2 wouldn't be selected.
Yeah, so maybe in the pre-training task, we'll find that gets usually will follow what tool. So based on the statistic reasons.
Probably.
So just look at the localized programs, we will see that gets dark is not ranking as high. It's not so potential, so promising as get 2. But from the overall sentence, get dark is supposed to be answered.
Yeah, maybe there is some way to show the following 4 position, but I didn't know how to show it. Here you can see the following the 4 word of the 2, but how to show the following top? Here is the top 4 behind the 2, but how to show the following top 4 about the get?
Maybe you need to double click.
Okay, maybe here.
Yeah, that does appear. That does appear in the big search, but it is not. I think the width of the line showing the probability, right? So they're saying that the probability of shooting dark is much smaller than shooting 2.
Yeah, from this.
Yeah, that is a quick remedy that we enlarge the candidate pool. But I think a more fundamental remedy from my perspective is that we need to look into more context. We might need to look into more context, but I don't know how to look. For example, on the street, suppose on the street is a more potential way, or if we, for each time we look into one step, and what if we look into 2 steps? There might be also a remedy, but I don't know. So anyway, it's good to know what is the problem.
Yeah. Okay. So this is a this is a real world example, and you can correct with print the duck.
Oh, by the way, so
Yeah,
is
you can-
that possible to deploy these tools by ourselves?
Yeah, because he gave us the code.
The
This
source
is
code,
the demo.
right?
Yeah.
This is demo. So I think we can set up the same tool so that both Yihao and both Yihao's customization that your code research can basically use this tool to investigate the problem.
Yeah. If you can change the word to the duck, and then it will.
I still have a very high probability.
Yeah, you will get.
So it means that if we look into local way, we remove, but we look into global way, now we can derive a very promising sentence.
Yeah. Okay. So maybe there's some question about the beam search. Maybe I will check whether how the beam search works in the after this presentation. Okay, here is some question. So there's another example here. Is the German is like here, and the gold label is we all live on a yellow submarine. And however, the prediction is we all live in a submersible, and there are some mistake on the word. So if you look at this tool, can you check whether the 4 parts are good or not?
So what your question is, what should we do to infer what is the problem of such a translation bug?
No, my problem is that how to use this tool to check whether these 4 parts are good or not. Yeah,
So
maybe I give an example. For example, you can see that if you the submersible the attention is good because in German U-boot means U-boot just means submarine. So if you check the attention, you can see the attention mechanism is good. So you can follow what I have said to examine the system is right.
Yeah, so in the end, volunteer to have a try to debug the sentence translation error. And then volunteer to have a try. If there's no volunteer, you can randomly pick a one.
Okay, maybe Ruofan, could you have a try?
Kind of which word is wrong?
You can.
Here the problem is the U-boot. In German, U-boot means submarine, but this mode predicts the submersible. So we want to check what part of the model is wrong.
Maybe decoder part.
Yeah, so how to check the whether?
Because you look at its neighbor, some of the time its neighbor has the submersible, some of the time it has submarine. So the decoder cannot distinguish these 2 words.
Yeah, I think so. So for example, if you look at the top K, you can see that the submarine and the submersible also have a very high possible. So the top K is not wrong. And if you look at the beam search, the submarine also is a candidate of the beam search. So the beam search is not wrong, because the beam search size is good because you can include the submarine word. However, if you look at the decoder, you can see that the submersible, the decoder hidden state submersible have some so the decoder can't differentiate between the submarine and the submersible. So maybe the decoder is not good. And if you look at the encoder, you can see that, sorry.
The U-boot is okay, right?
Yeah, the U-boot is okay. They are mostly they are U-boot. Also some other word, maybe it's not quite good. Yeah. So this means that the encoder or the decoder maybe can't quite sure about the meaning of the U-boot.
Okay.
Okay.
That's interesting explanations. And good question for answer.
Okay. So now we know how to use this tool. Here, another example is about data conversion. It's a quite simple task. Your input will be match 21 and 20,000, 2000, and then the output will be another formula of the date. And here we is the result. We can see that this example is want to prove the effectiveness of the attention embedding space and the neighbors list. And first we look at the attention. We can see that because the MA, the character M and the A is the same in the two examples. So the model mostly work on the R, C, and Y character. So that means the attention is good. And then for the embedding space, it just use what I have mentioned. You can see that in the embedding space, the Y and the R are far away, and the RCH are far away. That means these words have different meaning. However, like the same word, they have the quite near to each other, so close to each other, so they may have same meaning.
By the way, so do you know how long do we need to derive such a visualization system for a given subject?
I don't know, because actually the demo just gave us two examples.
Yeah,
so
yeah,
I just
the off-the-shelf. Yeah, we now deploy off-the-shelf solutions, because analytics need requires training, and also the beam search. And I assume that a lot of the intermediate result is cached, so that it's a proof result. But I have no concrete idea. If we want to deploy a system, suppose we have our own code search algorithm, code search models, and how likely and how instant will the tool, and how useful the tool will be considered in our own research.
Yeah, but for our code search problem, if you use the Siamese architecture, the congestive architecture, you can't use this.
We do not need the beam search definitely, but we can use the other part of encoding, decoding attention, so that would be important, right?
Yeah, but you didn't have a decode. Maybe I will see from.
And also I think that at least the attention is very important. How to match a piece of code with a piece of description, and why the code will be searched, and why do they think this code will be similar to this description? So those are these two will be at least the attention evidence be used to interpret. So,
for summarization, I think we can use this tool, but for code search, maybe it is needed to some change on the code.
Okay.
Okay. So finally, this neighbors, and you can see when predicts the A, because MA is the same word in the May and March. So they still, the model still didn't know how to predict May or March. And after you input the R, the model will know it is March or not the May. Okay, so it is just a very simple example. And the final example is the summarization. So we can just use this summarizing tool for the code summarization. And this here is the example. The source is Russia, blah, 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 defense minister, blah, blah, blah. And then the target is Russia calls for joint front against terrorism. And here, the summarization is want to compress the sentence to a more, you know, more, yeah, cause more small size, more short sentence. And this paper only gives some, some example to show this visualization tools work very well, and you can change the word to get a different result. For example, here, this model gets the result a bit long. If you change the if you change the for to the on, this will be much long because for the grammar you needed to cause on word leaders, blah blah blah. And if you change the first word to like Moscow, for example, in the media always use the capital name to represent a country. So if you use the Moscow or a simple word Russia, it will be much short. So you can change the word to get a different result. Okay, so this is the tool. And I just introduced how to use this tool, and what I have a short review on the sequence-to-sequence model and the attention mechanism. And then I introduced how to find out the encoder attention decoder top K and the beam search error. That's all for today's presentation. Thank you.
Yeah, I think that's a very good presentations, and I think they showed a lot of interesting too, but also some very fundamental basics that all of us to reconsolidate the memory. A really good presentations. Is there any questions for this talk? By the way, there's a new audience function. Do you have any questions here? Okay, maybe Changsheng is not here. Okay. Thanks, Yufan. Let's proceed to Yijie. Hello, Yijie. Yeah, please start. So maybe do you need to recap about this idea? So this work. So here, maybe you can start first. You can start the presentation, and if you need, I can complement or with my comments further the slides.
Okay, so hi everyone. Today I'll be presenting approaches and tools for automated end-to-end web testing. This paper was published in Advances in Computers, volume 101 in 2016. So these are the authors. So to start off, what is end-to-end web testing? So end-to-end web testing is testing a web application from the end user's point of view. So what we want to do in end-to-end web testing is we want to imitate what a normal end user would do to use the web application. So two aspects of automating end-to-end web testing are how to implement test scripts and how to locate web elements. So for implementing test scripts, there are two approaches. Being capture, replay, and programmable. And for locating web elements, there are also two approaches, which are DOM-based versus visual, which I'll explain a bit later on what they are. So for these four approaches, these four tools were used: Selenium IDE, Selenium WebDriver, Securely IDE, and Securely API. So for Selenium IDE, which is a capture, replay, DOM-based approach, I will show you.
So here I raised a question to some of the students. So for example, Darren, do you know about what is DOM? Hello, Darren.
The object model that's used to represent the website.
Yeah, so basically the HTML is used to present by the DOM, basically showing a tree structure. So when the user click certain buttons, basically it is the browser will know which object on the tree is being collected. So basically it will using the capture and replay task and tracking not the screenshot, but tracking the DOM elements being collected or interrupted. Have I made myself clear, or is there any confusion there?
No, I think it's quite clear.
Okay, please, then Yijie, please proceed.
Okay, so I will show a short demo with this YouTube video. Can you hear the video?
Not that clear, but maybe when you play, you can just explain a bit.
Okay, so this is what the Selenium IDE looks like. So you enter a URL and then you start recording, and then it will open up the web page. And all the actions you perform on the web page will be automatically recorded in the Selenium IDE. So if you click the username box, and then it will be displayed. Yeah. Then afterwards you can also modify all these values. So you can see like the web element locator is the ID of like each HTML element. Yeah. So I'll go back to the presentation. So next is Selenium WebDriver, which is using programmable approach and DOM based. As you can see, it's just like code. And then after that, Security IDE is using capture, replay, and visual approach. So you can see like compared to the Selenium IDE, which is like DOM locators, the Security IDE uses pictures. So it's like visual form. Yeah. And
so here is a small question. So is that possible to translate the recorded scripts into a programmable program Java and Python code?
I believe Selenium has the ability to do that, but I'm not sure about Security. So for Selenium, you can record the test, the capture replay, and then after that, it will be able to convert into the program.
So yeah, I'm thinking about it because we're talking about your phishing project. So we need to interact with the phishing web page, right? So I'm thinking about it. If you need to relieve your research effort, maybe if it is possible that you can just manually click a few interact with a few phishing web page, then we record the scripts of your interaction. Then we can generalize the interaction to all the other phishing web page. That might be an idea, but let's talk more in a bit.
Okay. Yeah, then next is Security API, which is programmable and visual based approach. And it also uses pictures as the locators. So the purpose of automating web testing is to ease the process of testing. So basically, like some benefits are that it can help to automate data-driven tests, where like you change like only the data, and also it ensures that the web app works across multiple stages of development or multiple releases. So moving on to the problems and challenges. So an issue is that across different stages of development, changes in the web application can break the test scripts. So so we need to repair the test script, so called. Yeah. So this work aims to analyze the strengths and weaknesses of the various approaches, and also understand which approach is more cost efficient and less fragile to changes in the web application. So first they selected 6 open source web applications from sourceforge.net. And then they built 4 test suites for each web application. And they standardized the programmable approach to use the page object pattern, which is like, as you can see here, this is a page object class. The home page is a page object. And then there are locators declaration, which is the, in this case, is the DOM elements. And then there are also page object methods like login, check log user, etc. And then for DOM-based approaches, they mainly locate by ID. So like as you can see, like this input tag has an ID of login field. So this login field is what they use to check. Yeah.
To locate the element and try
Yeah.
to click there. Yeah.
Yeah. So this part, it was a bit confusing, but it says that they executed the test suite against the second release of the web application and repair the failed test cases. So what I'm assuming is that the test suites are made so that it doesn't fail the first release, and then they test against the second release to see like what breaks.
And what's the definition of failure?
Failure means that so the assertions in the test cases like fail, I think.
And basically, how do they define a session? Or whether it will be successful, or given a login web page, whether it will be successful, like whether the user can successfully log into the web page, or
they'll look for like locators, like if it's for visual, then maybe they'll look for like login user, then the name. And then if it's like DOM based, then they'll try to find elements containing the user's name or something like that.
if it's not successfully found, it seems a failure, or
Yeah, if it cannot be found, then it's a failure. So for each test suite, they record the number of locators used and the number of locators broken and need to be repaired, and also the time taken to develop the test cases and the time taken to repair the broken test cases. So the question is, like, if you look at this graph, which approach do you think has lower development time? Yeah, does anyone want to answer?
yeah, is there a volunteer? So this is a very good question. And for you to recap, look at the chart and answer. Also, maybe check your memory. So which one is after and which one is programmable? Okay, there's a volunteer, Darren's. Darren didn't answer. So Darren's answer is programmable one.
Okay, so in this case, development time actually refers to like the initial development of the test suite. So it has to be from scratch. So actually the one that has lower development time is capture replay, which is Selenium IDE and Security IDE. I think it's because like it's easier for a tester to just click on elements on the web page and just record it, like instead of like having to make page objects and stuff like that.
Yeah. So I think Yijie's explanation is very intuitive. So from the very beginnings, the capture and replay, the user just need to click the buttons or type the input. Then the recorders will just record all the scripts, record all the actions, and consolidate into a script. That seems to be more convenient than the programmer to write each line of code to specify what action it is, right? Okay, let's proceed.
Okay, so if you look at the graph, the development time is shorter for capture replay and DOM based as compared to programmable and visual. Yeah, so I'll move on to the repair time. So if you look at the repair time graph, we can see that it actually takes much shorter time to repair the programmable scripts than the capture replay scripts. And also DOM based takes less time than visual, which which is because like, okay, I'll just explain this later. Yeah.
Okay.
Okay, so the next question is, among capture, replay, and programmable approaches, which is more efficient? You can like answer in like short term or long term or anything.
Yeah, so this is a kind of open questions. Everyone can share their own opinions. Yijie, maybe you can really pick one, or is there than one tier?
Uh,
Yeah, maybe you can choosing notice.
I'll pick Yuchen.
Hello, Yufan.
Hi. Okay. So I think I would consider programmable to be more efficient because after you set up the test suite, the fixing takes less time. So like the initial cost of setting it up becomes amortized against all the releases.
Yeah, that's correct. So through the experiments, they found that like programmer tests had higher initial development effort, which was between 32% to 112% more than capture replay. But afterwards, the maintenance effort was lower, saving between 16% to 51% after one release. So on average, programmable test suite becomes more efficient after 2 major releases. Yeah. Okay,
Yeah.
so I'll move on to the benefits of each type of approach. So for programmable, there's higher modularity and greater reusability of page objects. So like instead of having to like repair each test case one by one, you can just repair one page object and you can fix a lot of test cases. That's if you make good use of the modularity of the page objects. Like if you make a different page object for every test case, then you won't benefit lah. Yeah. Then locators in page objects also have like less duplication, so there's less locators needed to be repaired. So like in Selenium IDE, there were 727 broken locators out of 2,700. And then, but then in Selenium WebDriver is only 162 broken locators. So you can see like the effort needed to repair is much lesser for the programmable approach. And also for programmable approach, there's other functionalities such as like conditional statements, loops, exception handling, parameterization. Yeah. So benefits for DOM-based over visual approaches are that DOM-based require 45% fewer locators. So the visual approach requires a different visual locator for each change in state of an element. So for example, the question I used just now, I used the radio button. So like if it's a visual approach, we have to capture both the non-click radio button and also the click radio button, which is like a lot more locators. Requires a lot more locators. Yeah. Then for
So
DOM,
basically, the visual part is have to capture or remember the exact positions and where they should be clicked, right?
yeah.
So as long as a minor change of the layout, etc., then it's just broken.
Mm.
Yeah, but I think that is this paper published 4 to 5 years ago, but later there's some new computer vision based technique. Maybe such a problem can be mitigated. That means giving a buttons, the object detection model may be dynamically relocate where the button is. So maybe it will be the problems maybe mitigated, but we can discuss more later.
Okay. Then the next point is that DOM-based perform better with complicated interactions and also invisible elements. So like, for example, this was like on a web page and it was at the bottom of the web page. Then the visual-based approach will have to scroll all the way down to find this. But if it's a DOM-based approach, it just needs to look for the ID of this radio button. Yeah. So even if it's not visible, it can still find the element. Yeah. And then also DOM-based performs better with data-driven tests because it's easier to automate like different sets of data for the DOM-based. Like compared to the visual approach, you have to take a screenshot of everything. Yeah. So next, there are also some benefits for visual over DOM-based. So for visual, if there are changes in the HTML code but no visual change on the website, like no visual change in appearance, then the visual test will not break, but the DOM-based approach will break. This was shown in one of their experiments where I think the ID locators were using like an auto-generated locator. So when they added one extra locator, then the ID of everything changed. So they have to fix all the IDs. Yeah. And then also for visual approach, the pictures are much more comprehensible. It's like if you just look at the picture, you can tell like what's the difference between this and the current state of the website. So you can know like what's the issue and what needs to be fixed. Yeah. So for the summary of each approach, so the benefit for capture replay is that it has less time needed for initial development. So if it's a very small app or like it's not intended to be fixed beyond like what it originally is, then maybe capture replay can be considered, since it only needs to be used once. And then for like more complex applications, programmable will be better, especially if there's a high level of modularity, and it's better at data-driven tests as well. And the total effort needed to maintain in the long run is much lesser. Yeah. The next question is to fill in the boxes for this. Yeah. If anyone can annotate on the screen.
Yeah, anyone would like to have a try to compare the DOM-based and the visual-based approach? If there are no volunteer, Yijie, you can just randomly pick an audience.
Yufan, can you help?
Okay.
Okay, so she got everything except for one right, except for one wrong. So for the HTML only changes with no change in visual appearance, it's actually visual is better. Yeah.
So maybe you can specify the reasons. I think you have already mentioned, right?
Yeah, I explained just now.
So basically, for example, if you change the ID of DOM elements, from the visual part, it will not just it's a visual part. From the visual perspective, the appearance looks exactly the same, but it will influence the DOM scripts. But basically, the visual appearance will just be the same.
Yeah.
Okay.
Okay, so how do I clear the screen?
Yeah, I have cleared for you.
Okay, thank you. So the last part is overcoming the limitations. So since each method has like some pros and cons, there's a way of combining capture replay, programmable and DOM-based and visual approaches. And there's this tool that's been made. It's a GUI testing tool, automation tool called Renorex. And it is mainly capture replay, but you can incorporate programmable parts into it. Like you can upload, I think you can upload coded scripts into it and you can incorporate. And also it modularizes the process. Like if you make the same steps, the same sequence of steps for like 2 test cases, it will modularize that sequence of steps so that you just need to fix one of them. Yeah. And then yeah. And then for the next point is automatic test case repair, which is a suggestion system to suggest ways to repair the test script. So this will reduce the repair time needed. Yeah. Then the last point is the automatic migration from Selenium IDE to Selenium WebDriver. So the capture replay will be converted into a script, so you can change it, you can modify it in Selenium WebDriver. Yeah. So the takeaways are that DOM-based tools are often more robust and require less development and repair time than visual tools. With the exception, like what I said just now, if the ID locator is changed, that is automatically generated, and one change can cause all of them to break, then of course in that case visual tools will be better. And then for programmable approach, it benefits from greater modularity, and it creates more cost savings in the long run.
Yeah, that's a very clear presentations and prepare very excellent questions. Compared to Yufan's presentation, which is more research oriented, and Yijie's this talk is more maybe education oriented. So maybe some of you are familiar with web testing, maybe not, but it's good for you to know that, especially in industry, how do we maintain the scripts and the test cases for testing the web UI address. But more importantly, EGSFIP research is more maybe facilitate or utilize these kind of tool to interact with the web page and to confirm what is the dynamic intention of the website. So this is basically a software engineering technique, but it is fundamental enough, and there will be incorporated some script incorporated, but maybe we also will combine this with object deep learning based approach to interrupt and identify, recognize the malicious intention of web, or the intention of malicious web pages in a smart. Okay, so is there any questions for EGS presentation? Okay, yes, if there are no questions, I think we can call the day. Today, I think both Yijie and Yufan present very excellent presentations, and they do provide a very informative and all very interesting debate. Thank you, and that's for today.